Hello everyone, my name is Yuwen Heng. The title of our paper is Enhancing Material Features Using Dynamic Backward Attention on Cross-Resolution Patches. The presentation for today contains three sections. First, I will introduce dense material segmentation, the material segmentation applications, and related work. After the introduction section, I will go through our contribution, the dynamic backward attention transformer, or DBAT for short. Finally, I will conclude our work and end this presentation with the limitations and a future work plan, which is related to network interpretability. So, the dense material segmentation task aims at assigning a material category to each pixel of the input image. A well-designed model should be able to identify the common materials in daily scenes, including wood, metal, glass, etc. Take the kitchen image as an example. The model should be able to identify the glass-made microwave oven screen and the wooden cupboard respectively. Now, for applications, the predicted materials can be used to guide robots to perform certain tasks, like grabbing tools and collecting nuclear garbage. The segmented image can also facilitate material-dependent tasks. For example, estimating acoustic properties to synthesize immersive sound, or estimating optical properties for physical-based rendering. The figure here illustrates a typical pipeline to synthesize sound. By mapping the predicted material labels to the 3D room model, modern software can calculate how sound interacts with the materials and generate immersive sound with audio reflection and reverberation. However, material segmentation is not a trivial task. Since a specific material can have a variety of appearances, such as shape, color, and transparency, annotating the images densely becomes a tough task. As a consequence, it is difficult to acquire densely labeled material datasets. To achieve a high performance for material segmentation task, an intuitive method is to combine material and contextual features. Now, the global or semi-global contextual features, which is taken from the full image, like scene and object, can limit the possible materials that appear in the given image. Now, the local material features hidden in the image patches, like material texture, can generalize the network to unseen images. Now, the question is how to properly combine the contextual and material features. An example is the context-aware material segmentation network, or ChemSegNet. It has two input branches to process both contextual and material features. During training, the contextual and material features are shared between the global and the local branch respectively. Although this network architecture can achieve a good performance, the patch resolution is fixed, which does not consider the area that the material region can cover. Now, instead of fixing the patch resolution, our DBAT investigates how to predict the materials from cross-resolution patch features. It takes 4x4 patches as input and increases the patch resolution in the encoder by merging adjacent patches at each transformer stage. This way, it is possible to aggregate cross-resolution features with a single branch encoder. Now, the backward attention module aggregates the cross-resolution patch features with predicted per pixel attention masks. Finally, the feature merging module with a residual connection ensures that the dbyte learns complementary features. Now, let's take a closer look at the backward attention module. It first gathers the cross-resolution features extracted from the backbone encoder. Then the attention module predicts the attention masks from map 4 here. After that, the network applies the attention masks to each feature map with the pixel-wise production operation. Then the feature map are aggregated with a summation operation. The overall process can be described with a weighted sum equation where the weights are predicted attention masks. Now, for the feature merging module, in order to control the learning process, we use the 4-stage feature map to guide the aggregation of features. This module is based on an attention mechanism as well. The multiplication of the outputs from query and the key matrix produces the pairwise attention weights. The attention weights look for information in the output from value matrix V, which is processed from the aggregated features. With the residual connection here, the useful information from the aggregated features is injected into map 4, which ensures that the DBA module learns complementary features. Now, our dynamic backward attention transformer achieves the highest accuracy on the local material database. Its performance is close to the multi-branch ChemSegNet DBA on the Open Surfaces dataset, with 9.65 more frames per second and around 20 G fewer flops. For qualitative evaluation, in this image, the boundary between the wooden window frame and glass in DBA segmented image is more adequate than the segments predicted by other networks, such as SwinT and ChemSegNet DBA here. In addition to the performance evaluation, we also did some analysis to understand the behavior of the network. The first I want to show you is the centered kernel alignment, the CKA matrix here. It measures the similarity of extracted features between two arbitrary layers. In this heat map, the brighter the color is, the more similar features to layers extracted. The darker region around 0.140100 in figure B indicates that our dbyte learns different features compared with its encoder output. It is discovered that the material covering multiple small objects and the material covering a small area tend to depend on the features extracted from a small patch resolution. For example, the first column image in this figure highlights the regions that the network concentrates on. The wooden area in the first row covering both the desk and the floor, the wooden chair and the fabric floor are mutually overlapping in the second row. These objects or material regions are mutually overlapping, and only small image patches can isolate them at the boundaries. Figure A here shows the average attention weights for the 4 feature maps extracted from the encoder. The box plots in Figure B show the equivalent patch size used to extract features from the feature map 1 to 4. And to further illustrate the effect of the dynamic backward attention module, the similarity scores comparing one layer with map 1, 2, 3, 4 from the CK matrix is reported in figure B here. Together, they show that the aggregated features depend on information from shallow layers to improve the network performance. To conclude, we proposed a single branch network to enhance the material features dynamically by aggregating the cross-resolution patch features. It beats all chosen models that can serve real-time applications on 2 datasets. Its mechanism is illustrated by visualizing the attention marks and the CKA heat maps. Although the D-byte achieves an accuracy above 85%, the material and contextual features are not semantically explained. As a consequence, it is unclear how much the network relies on material and contextual features respectively. Therefore, in the future, we plan to interpret the features with semantic labels. One of the possible choices is the network dissection method, which aligns the features with the semantic labels that overlap most with the extracted features. That's all for my presentation today. Thanks for listening. If you have any questions, we can chat in the website.